So, we had been discussing conductors and two properties of conductors that we discussed were: number one, a conductor is an equipotential. So, the whole body is on one potential, its surface is an equipotential surface. Equivalently, there is no charge inside a conductor, or that a conductor, and that follows from E being 0, and therefore, Gauss's law gives this, and all the charge is on the surface. And second point that we discussed was that a cavity inside a conductor is field free. So, let us start this lecture with a problem involving a conductor, and the problem that I am going to solve is from the book of Zangwill, Modern Electrodynamics. It's an example given there. Suppose there are two conductors, spherical, of radius r1 and radius r2, and they are at vectors r1 and r2 from the origin. That means, the centers of these, right? So, centers are at r1 and r2, and so they are put in a uniform electric field E. Then, if the question is, if the distance between the spheres is much larger than r1 or r2, we will use this approximation, and what are the charges on the two spheres. So, we will be using that approximation, and when I use it, I will let you know how we are using it. So, what is the physics behind this? So, physics says that the charges will move from, I forgot to tell you, these conductors are also connected by a wire. Okay, so, they are connected by a wire. The spheres are connected by conducting the charges will move from one sphere to the other because of the field. And how do they move? They move through the wire. So, we will make an assumption that there is hardly any charge on the wire. It is assumed, because a thin wire, its capacitance may be very low. So, charges move from one sphere to the other because of the field. And how long does it take place? Until the two spheres are at the same potential. What that would mean? This would imply no field in the wire, because delta V is 0, and that will happen if there is no field in the wire, right. So, they will keep on moving. So, the physics is that the charges should be such that the potential between the two spheres is potential difference between the two spheres is 0. So, 1, there will be a potential difference due to the electric field. 2, there will be potential on each sphere due to the charge on it. And 3, there will be potential on each sphere due to the charge on the other sphere. And it is this third point, the third contribution will be neglected. Because the distance between the spheres is large. Otherwise, the third point will also contribute, but we are going to ignore it. So, let us see what is the picture that we are making now. Is that here is one sphere at R1, here is another sphere at R2, radius of the first one is R1, radius of the second one is R2, and here is this uniform field. Let us calculate delta V due to the electric field. So, I am going to calculate V at 2 minus V at 1 is equal to V 2 at the center of sphere 2 minus V 1 at the center sphere 1. You see, I am calculating it only at the center, because the entire sphere is an equipotential. Therefore, no matter where I calculate it, the potential would be the same throughout that sphere. So, I will choose a convenient point which happens to be the center. So, V2 minus V1 by definition will be equal to minus E R2 minus R1 E dot, which is minus E dot R2 plus E dot R1. This is the work done by us if I were to move a charge from unit charge from the center of first sphere to the center of the second sphere. So, this is contribution 1. Now, let us calculate. So, let me call this 1. Let us now calculate contribution 2, and that is V1 due to the charge on sphere 1. So, here is sphere 1, and the charge, whatever, suppose the charge is Q1, it is going to be all on the surface. So, all this charge will be on the surface. Let us say it is plus, because all the charge resides on the surface, and that is very convenient, because then I can calculate the potential at the center. The potential at the center V1 would be, suppose I take a small portion here which has some charge delta Q1 in the ith portion, divided by the radius is the same R1, and I sum over I. So, this will come out to be Q1 over R1. And similarly, V2 therefore will come out to be Q2 over R2. The other one is, this is R1, V2 over R2, and since Q1 and Q2 together are 0, because net charge is conserved, this is equal to minus Q1 over R2, and therefore, the second contribution V2 minus V1 is going to be Q1 over R1 minus Q1 over R2. So, net potential difference, net difference between the two spheres is going to be minus E dot R1, that was R2 I think, plus E dot R1 plus Q1 over R1 minus Q2 over R2, and this should be 0. Sorry, this is Q1 again. So, I get Q1 I think I made a mistake here. So, let me just cut this. The mistake was right here. This should have been Q1 over R1, and the other one is negative. So, this is plus Q1 over R2, and therefore, net potential difference will be minus E dot R2 plus E dot R1 plus Q1 over R1 plus Q1 over R2 is equal to 0. And this gives me Q1 R1 plus R2 over R1 R2 is equal to E dot R1 minus R2. And therefore, the answer comes out to be Q equals E dot R 1 minus R 2, this is Q 1, divided by R 1 R 2, and here I have R 1 plus R 2. So, what we have found is that if I have these two spheres at distances R 1 and R 2 from the origin in a uniform field E, then, and the radius of the first one is R 1, radius of the second one is R 2, then the charge on the first one is going to be Q 1 equals E dot R 1 minus R 2, R 1 plus R 2 over R 1 R 2, and on the other one is going to be minus Q 1. So, what I like you to do is check this answer for different combinations of R 1 and R 2 and R 1 and R 2, keeping in mind that the distance between the spheres is kept very large. So, this is one example where I have shown you how I can exploit the equipotential nature of a sphere, and also that the charge resides on the surface of this sphere. So, we now come back to properties of conductors. So, in the previous lecture I had counted 3. So, I am going to now write number 4, and that is going to be if we keep a charge in an arbitrary shaped cavity inside a spherical conductor, the potential and therefore the field outside the conductor is such as if the charge was situated at the center of the sphere. So, let me explain what it means. So, suppose I have a sphere of some radius r, and I make a cavity inside, the rest is still solid, and I put a charge q inside this cavity. Then for outside world, the outside world here, it is as if the charge is uniformly spread over the surface, or equivalently it is sitting at the center of the sphere. Let us prove that. I can argue in two different ways. So, here is this spherical conductor with a cavity inside and a charge inside somewhere. Now, no matter what you do and where this charge is located, if I take a Gaussian surface inside the conductor, any shape, integration d E dot d s is going to be 0 for any Gaussian surface inside the conductor. This means net charge enclosed is 0, and this implies further that the charge on the cavity surface is minus q. So, if you look at the cavity surface, I am going to go back to the picture, there will be this charge, net charge minus q. So, leftover charge for the rest of the bulk is plus q. The charge left in the rest of the, it is not rest, charge left in the bulk of conductor is plus q. Question is, how is this charge distributed? Remember, what we learned earlier is there can be no charge inside the bulk. Number 1. Number 2, all the charge q therefore must be on the surface, and should be distributed in such a manner that it gives E equal to 0 in the bulk. Because remember, the charge inside the cavity and the surface charge induced on the cavity surface already gives 0 field. So, any extra charge has to give this field to be 0 no matter what, and this can happen. So, this happens if q is distributed uniformly over the surface. This is very logically as follows, because this problem we have solved many times. So, let us see what is the picture that is emerging. The picture that is emerging is that here is this conductor, here is this cavity inside, here is this charge q somewhere inside, and because of this there will be this negative charge all around on the cavity surface, and there will be positive charge total q on the outer surface, and it will be distributed uniformly. So, as far as the outside world is concerned, the field due to this thing in the cavity and around it, field due to this q and plus q, this gives me E equal to 0. So, the field is going to be only due to this q out here, right, and it is going to be spherically symmetric because charge is spherically symmetric, and therefore, E outside is equal to 1 over 4 pi epsilon 0 q over r square. R is equal to, in the radial direction, distance from the center of the sphere. Very clean. So, that is one way of looking at it. Let us look at another way of looking at the same problem. So, this is clear, right. I mean, the thing is, wherever I put the charge, wherever is the cavity, the charges induced on the cavity make sure that the field outside is 0, and then whatever leftover charges, it distributes itself symmetrically over the surface, because that only gives you additional 0 field inside the bulk, and therefore, outside it gives you a field which is as if the charge is sitting at the center. Another way of looking at it is mathematical. So, I have this spherical surface, and I know that V is constant throughout. So, what do we have now therefore? I have the potential to be V 0 on the surface as inside. So, let this constant be V 0, and the Laplace equation outside is del square V is equal to 0, and V equals V 0 for R equals R. The only solution, and you can check for this, is going to be V R is equal to V naught R over R. Okay. This satisfies the boundary condition. And a Laplace's equation, and therefore, this is a unique solution, and this implies the field outside, which is minus grad V, is going to be V naught R over R square R, and by Gauss's law, E dot ds is equal to q enclosed by epsilon 0, because charge enclosed anyway is q, gives V naught equals one over 4 pi epsilon 0 q over r, and the answer follows. So, we have done it mathematically, we have also argued, so that you develop an intuitive feeling about the electrostatics that we are doing. Next, I am going to discuss, suppose I have an arbitrary shaped conductor and give it some charge q. So, this is problem number 5. I have given it some charge q. So, then the claim is that on an arbitrary shaped conductor, if charge q is given, then the field will be largest near sharp corners, and this also implies that charge density, and since this is a conductor, it is going to be surface charge density, because charge is going to reside on the surface, is maximum near the sharp edges, corners. And this is quite simple to see. For this, I will argue it in a slightly different way. Suppose I have two spherical conductors, one of radius r 1, another of radius r 2, and I gave the same potential to both of them, V 0. and I want to find out what are the charges on the 2. So, V 0 is going to be 1 over 4 pi epsilon 0 q 1 over r 1 or q over r 1, suppose the charge is q, which is also equal to 1 over 4 pi epsilon 0 q 2 over r 2. It should be q 1. And this gives me that q 1 is equal to q 2 r 1 over r 2, or q 1 is equal to V naught r 1 times 4 pi epsilon 0, or q is proportional to r. And therefore, the electric field on the surface E, which is 1 over 4 pi epsilon 0 q 1 over r 1 square, E 1 is going to be equal to 1 over 4 pi epsilon 0 r 1 square V naught r 1 4 pi epsilon 0 over r 1 square. 4 pi epsilon 0 cancels, and you get this equal to V naught over r 1. So, what you find is for the same potential, electric field is proportional to 1 over r. So, in this case, where I had two conductors, spherical conductors, both have potential V 0, radius is r 1 here, radius is r 2 here. The electric field here will be much stronger than in the first case. Larger the radius for the same potential, smaller is the field on the surface. And remember, E is equal to sigma over epsilon 0 near a surface, conducting surface. So, sigma is also proportional to 1 over r. Now, let us look at this conductor of arbitrary shape, and I give it some charge q. The potential is going to be the same, some V 0, and it should be the same throughout. Therefore, wherever the radius of curvature is small, field is going to be strong. Wherever the radius of curvature is large, field is going to be weak. Hardly any field, hardly any field. Little stronger here, again less, and again strong here, and this is a sharp edge, so very strong here. And similarly, sigma theta is going to be similarly large or small depending on the radius of curvature. So, sigma theta is going to be very large here. Let me show it by a thick line, then it becomes thin line, and maybe little thicker here, then very thin, very thin, maybe little thicker here, very thin, and very thick here again. So, charge density concentrates near the surfaces where the radius of curvature is small, electric field is very strong, and this is applied in making lightning conductors. So, what you do is on the top of the houses, you put a conductor with very sharp edge, so that when there is lightning, it will induce a lot of charge near the edge, field will become strong. So, all the current will go to this point and then go to the ground through the connecting wire. right. So similarly, when you must have talked about Van de Graaff in your BSc or MSc, where a conveyor belt is charged and is charged through very fine comb, because charges come near the edges of the comb and then get transferred. Whenever you want to transfer charges, you make a very, very fine comb. And similarly, any charging device has these brushes, which are very thin wires, and near the comb, there is this charge which is transferred. So let me conclude this part of the lecture by saying that we discussed two more properties of conductors. One was that a charge in a cavity made in a spherical conductor behaves as if it is at the center of the sphere, and two, that charge on an arbitrary shaped conductor distributes itself so that surface charge density is maximum near the sharp edges, corners. This is basically to make the whole surface equipotential or keep the field 0 inside. So these are two things, and in the next lecture I will discuss about forces that arise when you charge a conductor. Thank you.